In 1994 marked the beginning of a railroad revolution that would destroy EMD's 60-year dominance. Two manufacturers battled for control as railroads demanded radical solutions to mounting operational costs. EMD controlled the industry with their proven SD40-2 and reliable DC motor technology that every mechanic understood. GE was the persistent underdog, improving their -8 lineup while developing experimental AC traction that most railroads considered risky. Within 5 years, one locomotive would flip this power dynamic completely. This is the story of how GE's AC4400CW didn't just win market share, it destroyed EMD's railroad empire forever. Electromotive Division owned North American railroading as the 1990s began. Complete dominance, unquestioned supremacy. The SD40-2, launched in 1972, had become America's freight workhorse. Over 3,900 units delivered. This locomotive's 3,000 horsepower output, 6-axle configuration, and legendary durability created standardization levels the industry had never seen. The SD40-2's success came from EMD's bulletproof 645 engine paired with proven DC traction motors. The 16-cylinder 2-stroke 645E3 generated 3,000 horsepower at 900 RPM. The D77 traction motors delivered power through electrical systems that every railroad electrician could repair blindfolded. Simple architecture. A main generator connected directly to traction motors through straightforward control circuits. Fleet standardization was EMD's unbreakable advantage during this era. Burlington Northern ran over 940 identical SD42s. This created massive economies, bulk parts ordering, universal maintenance protocols, simplified crew training. A railroad could maintain hundreds of locomotives using identical procedures, parts inventory simplified, training costs minimized, operational predictability maximized. But General Electric had been closing the gap steadily throughout the -8 era that started in 1987. The -840CW, introduced in 1989, combined 4,000 horsepower from the 7FDL16 with microprocessor controls managing excitation, wheel slip, and auxiliary systems. Upgraded electrical architecture improved reliability and diagnostics beyond earlier GE offerings. GE's commitment to 4-stroke diesel development was paying off. The 7FDL engine delivered superior fuel economy compared to EMD's 2-stroke 645. Electronic controls provided diagnostic capabilities that simplified troubleshooting. The -840CW ran longer between major overhauls. When failures occurred, microprocessor systems pinpointed problems faster than EMD's analog technology could. Railroad operations departments were demanding changes that would force both manufacturers to evolve or die. Train weights were climbing as railroads chased productivity gains. Coal drags routinely hit 15,000 tons. Intermodal consists approached 10,000 tons. Heavy trains required multiple locomotives, but additional units meant higher crew costs and operational headaches. Railroads wanted a breakthrough. Fewer, stronger locomotives handling heavy consists without wheel slip or grade stalling. Traditional DC traction motors faced fundamental physics limitations in adhesion, converting engine output into pulling force without spinning wheels. When a DC motor started slipping, it continued until power dropped, preventing locomotives from utilizing full rated capacity. Wheel slip cost railroads serious money beyond operational frustration. Slipping wheels wore rapidly, forcing frequent replacement of expensive wheel sets. Slip events damaged track and wasted fuel as power spun wheels instead of moving tonnage. Railroad maintenance departments calculated that eliminating wheel slip could save thousands per locomotive annually in wheel and rail costs alone. Diagnostic capabilities were becoming critical as railroads slashed maintenance staffing and consolidated repair shops. EMD locomotives used analog electrical systems requiring experienced electricians for troubleshooting. Fault diagnosis involved time-consuming testing procedures. Railroads wanted locomotives that self-diagnosed problems and delivered clear information to maintenance teams. GE's answer was the AC4400CW, a revolutionary machine incorporating AC traction technology developed from their industrial motor expertise. Testing began in 1993. Production started in 1994. The AC4400CW generated 4,400 horsepower from the proven 7FDL16, while using AC traction motors that fundamentally changed how locomotives converted power into pulling force. The AC4400CW's core innovation was its AC traction system. Inverters converted the locomotive's DC electrical power into variable frequency AC for traction motors. Each motor had dedicated inverter control. enabling precise speed and torque management impossible with DC systems. The inverters used gate turn-off thyristor technology to create variable frequency AC for individual motors, allowing precise torque and speed control. The AC traction motors themselves were three-phase induction motors operating on completely different principles than DC motors. Rather than brushes and commutators like DC motors used, AC motors employed electromagnetic fields to induce rotor rotation. This eliminated constant brush maintenance required by DC motors and allowed motors to operate at dramatically higher power levels without overheating. AC traction's adhesion advantages were revolutionary. When an AC motor began slipping, the inverter instantly reduced power to that specific motor, while maintaining full power to remaining motors. This individual motor control meant locomotives could utilize nearly 100% of rated power without wheel slip. Compared to DC locomotives typically limited to 75 to 80% power utilization before slipping occurred, the performance gap was massive. The AC4400CW's continuous tractive effort rating hit 166,000 pounds compared to just 83,000 pounds for EMD's SD60. Despite similar weights, the GE locomotive pulled twice as hard at low speeds without slipping. Perfect for starting heavy consists and climbing steep grades where wheel slip was most problematic. GE designed the AC4400CW specifically for large fleet operations, incorporating features appealing to railroads running hundreds of identical units. Modular electrical systems use standardized components for quick replacement. Microprocessor controls provided comprehensive diagnostics that simplified troubleshooting and maintenance planning. The 7FDL16 engine in the AC4400CW incorporated decades of four-stroke development lessons. Electronic fuel injection delivered precise fuel metering across all operating conditions. Engine management systems optimized performance for fuel efficiency and emissions compliance. The engine ran 92 days, or 25,000 miles between major inspections, significantly longer than EMD's two-stroke designs. CSX Transportation became the first railroad fielding AC4400CWS in regular Class 1 service during 1994, ordering 25 units for evaluation in coal service between West Virginia and Virginia. These locomotives were assigned to CSX's heaviest coal trains, where adhesion advantages could be fully tested against existing EMD power. Early results generated immediate interest across the industry. CSX reported single AC4400CW units, replacing pairs of SD42S on many coal trains, slashing crew costs and improving operational flexibility. The locomotives started 15,000-ton coal trains on 1.8% grades without helper locomotives, something requiring multiple DC units or additional helper power. More critically, AC4400CWs demonstrated remarkable performance consistency. Unlike DC locomotives performing differently based on rail conditions, weather, and wheel wear, AC units delivered predictable tractive effort, regardless of operating conditions. This consistency let dispatchers plan train operations with unprecedented precision. Canadian Pacific's decision to order AC4400CWs in bulk during 1995 proved AC traction was ready for mainstream adoption beyond experimental service. CP ordered 133 AC4400CWS in their initial purchase, the largest single AC locomotive order at that time. This order showed a major railroad was betting their operations on AC technology. CP's order carried particular significance because it came from a railroad known for conservative locomotive purchasing. Canadian Pacific had been primarily an EMD customer for decades, operating large SD40-2 and SD60 fleets. Their switch to AC power reshaped the locomotive industry, signaling AC traction had moved from experimental to proven. Canadian Pacific locomotives were assigned to grain service between Prairie provinces and Vancouver, where their ability to handle long, heavy trains over mountain grades provided immediate benefits. CP reported AC4400CWS could handle 8,500-ton grain trains over Rogers Pass, with 2 units compared to 3 SD40-2s required for identical trains. Union Pacific began evaluating AC4400CWs in 1994. Initially ordering 50 units for testing in coal service from Wyoming's Powder River Basin. UP's coal trains were among North America's heaviest, routinely exceeding 15,000 tons. The railroad sought ways to reduce locomotives per train while maintaining schedule reliability. AC traction's operational advantages became clear as railroads accumulated service experience with the AC4400CW. Higher adhesion meant fewer locomotives needed for heavy trains, reducing both capital costs and operating expenses. A typical 15,000-ton coal train requiring 4 SD42s could be handled by 3 AC4400CWs, a 25% reduction in locomotive requirements. Adhesion advantages were most pronounced in challenging conditions. On wet rails where DC locomotives slipped continuously and required reduced power, AC locomotives maintained full tractive effort without wheel slip. Trains maintained schedules even in adverse weather that would slow or stall DC-powered consists. Continuous tractive effort capabilities eliminated many helper locomotive requirements that added operational complexity and cost. The AC4400CW maintained 166,000 pounds of tractive effort from 0.5 to 11 miles per hour, compared to DC locomotives only maintaining maximum tractive effort at very low speeds. This extended high tractive effort range meant AC locomotives pulled heavy trains up long grades without stalling or requiring assistance. Duty cycle economics were compelling for railroads focused on reducing operating costs. Fuel consumption per ton-mile improved because AC locomotives operated at higher power levels without wheel slip, eliminating fuel waste from spinning wheels. Norfolk Southern reported 8 to 12% fuel savings when replacing SD42s with AC4000 CWs in coal service. Wheel wear reduction provided another significant cost advantage. CSX reported 40% reduction in wheel replacements with AC power versus DC, saving thousands per locomotive annually in wheel costs and shop time. Microprocessor-based control systems provided diagnostic capabilities that revolutionized locomotive maintenance. The AC4400CW's computer systems continuously monitored engine performance, electrical systems, and mechanical components, storing fault data accessible through handheld diagnostic tools. This eliminated much troubleshooting guesswork. Fault diagnosis taking hours with analog DC systems could be completed in minutes with the AC4400CW's digital systems. Locomotive computers identified specific failed components, predicted impending failures, and provided maintenance recommendations based on operating history. This predictive maintenance capability let railroads schedule repairs during planned maintenance windows rather than dealing with unexpected service failures. Standardized diagnostic systems also simplified maintenance training and procedures. Rather than requiring experienced electricians understanding different locomotive electrical system nuances, railroads could train technicians using standardized diagnostic procedures working consistently across entire AC4400CW fleets. The AC4400CW's success created a cascade effect, fundamentally shifting locomotive procurement patterns across North American railroads. Orders in the mid to late 1990s increasingly favored GE's AC technology, with major railroads placing orders for hundreds of AC4400CWs as they experienced operational benefits firsthand. BNSF, formed by the 1995 Burlington Northern and Santa Fe merger, became GE's largest customer with orders exceeding 1,000 AC4400CWs between 1995 and 2004. BNSF's decision to standardize on AC power for coal and grain operations created enormous scale effects that locked in GE's advantages in manufacturing costs and parts availability. Scale effects worked against EMD as GE's production volumes increased. Higher production volumes let GE negotiate better supplier prices, invest more heavily in manufacturing automation, and spread development costs across larger unit numbers. These advantages made GE locomotives increasingly price competitive while maintaining technological superiority. EMD's response with the SD60 and early SD70 series looked incremental compared to the revolutionary change AC traction represented. The SD60, introduced in 1984, offered 3,800 horsepower from an improved 710 engine but still used conventional DC traction motors with inherent adhesion limitations. The SD70, introduced in 1992, provided 4,000 horsepower but remained fundamentally a DC locomotive competing against AC technology. EMD's high horsepower 265H engine and SD90M ACH locomotives absorbed significant engineering resources and management attention during the mid-1990s. But these programs were troubled from the start. The 265H engines suffered reliability problems, damaging EMD's reputation. The SD90M ACH's 6,000 horsepower rating proved more than most railroads needed or could effectively utilize. The SD90M ACH program's problems diverted resources from developing competitive AC locomotives, allowing GE to establish an insurmountable AC technology lead. While EMD struggled with the 265H engine, GE was refining AC traction systems and building manufacturing capacity to meet growing AC 4400CW demand. Canadian National's decision to purchase 320 AC 4400CWs between 1996 and 1999 demonstrated AC traction had become preferred technology for heavy freight operations. CN's order was particularly significant because it represented a complete fleet renewal program based on AC technology, replacing older EMD power with standardized GE units. Union Pacific's massive AC4400CW orders, totaling over 1,000 units by 2000, cemented GE's position as dominant locomotive manufacturer. UP's decision to standardize on AC power for coal operations created North America's largest single fleet of identical locomotives, providing unprecedented economies of scale in maintenance and operations. By decade's end, locomotive procurement had tilted decisively toward GE and AC traction technology. The AC4400CW had proven AC motors could provide significant operational advantages over DC technology. GE's manufacturing scale and technological leadership made them the preferred supplier for major railroads. The transformation was complete when even traditionally EMD-loyal railroads like Norfolk Southern began purchasing AC4400CWs in large quantities. NS ordered 200 AC4400CWs in 1999, acknowledging AC technology had become essential for competitive freight operations. EMD's market share collapsed from over 70% in the early 1990s to roughly 30% by 2000, a dramatic reversal reflecting the industry's embrace of AC traction technology. The company dominating locomotive manufacturing for over 50 years found themselves playing catch-up to a competitor that had successfully revolutionized railroad motive power. The AC4400CW didn't just win a technology battle, it destroyed a monopoly that seemed unbreakable just 5 years earlier.